All right, guys, so we're going to discuss a couple more questions, and we're going to really dive into make sure that you understand the concepts behind enantiomers, diastereomers, same structures, or if we're dealing with different structures, right? So in general, for the most part, if you're dealing with the same structure, it should be pretty apparent, right? You're going to look for connectivity. You're going to look to see if the RNSs are the same, if there are chiral centers. And sometimes it will be very apparent to you, right? If they're different compounds, then you know that they have different molecular formulas or something going on that's going to make them different. And enantiomers, remember, they are going to have the same connectivity. You're going to have opposite R and S at every single chiral center, right? Now we're going to discuss about the caveat that comes with a diastereomer. Now, the one thing about a diastereomer is that there must be at least there must be more than one chiral center, right? If there's only one chiral center, no matter how complex the molecule is, if there's only one chiral center, then you cannot possibly be a diastereomer. You have to have more than one chiral center to be a diastereomer. And you have to have opposite RNS at least one of those chiral centers, and then if you have the same RNS at another chiral center, that's perfectly fine. Remember, if you're dealing with two or more chiral centers in a molecule, right, you pretty much only have two options, an enantiomer or a diastereomer. If you don't have opposite R and S at every single chiral center, then that automatically lets you know that it's a diastereomer. There's no other thinking you have to do, nothing else you have to process. If you don't have an opposite R and S at every single chiral center, if you're dealing with more than one chiral center, it's automatically a diastereomer. But if you do have say for instance 2 or 3 chiral centers, and you have opposite RNS at every last one of those 2 or 3 chiral centers, then you're automatically an enantiomer. So that really helps simplify the amount of thinking you have to do, because there's only two options. So now let's dive right into the first example here, right? So again, remember, we always start off with our chiral center, and we see that we have four different functional groups, or 4 different atoms, 4 different, whatever you want to say, 4 different things around our center chiral center, right? And then here we also have 4 different things around our carbon as well. Therefore, we know that this carbon and this carbon can constitute as our chiral centers, right? What else do we know? We have a CN bond over here. We have another we have a chlorine group over here, a methyl and a hydrogen. Here we have a CN, chlorine, methyl, and hydrogen. So we have the same molecular formula, right? We also have the same connectivity, right? Because these 4 groups are still all connected to the carbon, as same with over here, right? There's not a different molecule here that's connected to the carbon. It's a CN, it's a chlorine, it's a methyl, it's a hydrogen. CN, chlorine, methyl, hydrogen. Therefore, we have the same connectivity, right? The only difference is how these molecules are arranged in space, which means now we have to look at the optical activity and look at RNS to determine if these molecules, right, we know that they are stereoisomers, right? So we had to look to see if these molecules are going to be enantiomers or diastereomers, right? Right off the bat, we know they can't be diastereomers. Why? Because there's only one chiral center. So we're really looking to see if these molecules are going to be enantiomers, or if they're identical molecules, or if they are, I guess those are the only 2 options, right? Because we know they're not different molecules. So we're just looking to see if they're enantiomers or the same molecule, essentially, right? So let's go ahead and do the same thing we did to figure out an RNS in the last video. We have 1, then we have 2, right? So we know that, let's go in depth a little bit more about this, right? So we start off with 1 because chlorine is our highest priority. Now we have a tie between a carbon and a carbon. Remember, the Me, the methyl group, is going to constitute as a CH3, right? We're going to have 3 hydrogens here, right? And then this CN group, right, it is a triple bond to nitrogen, and you can kind of think about that as having 3 nitrogens, right? So we know we're comparing a carbon to a chlorine to a hydrogen. The highest is going to be chlorine. Then we move on to the next. Carbon to carbon, it's a tie, right? Then we move on to the next atom from those 2 carbons. Hydrogen versus a nitrogen. Nitrogen wins, therefore this is 2. This is 3, and then of course our hydrogen is always going to be 4. We draw the arrow around, we see this is going clockwise, right? Where's our hydrogen? It's on a dash, right? Which means our lowest priority is on a dash, therefore we do not have to switch this from R to S. This stays at R, right? Let's go over here and do the same thing. 1, 2, 3, and a 4. We know this is going counterclockwise, right? Now our hydrogen is on a what? Dash, right? Since our hydrogen is on a dash, that means our lowest priority group is on a dash. Therefore, we do not have to invert the stereochemistry. So this is going counterclockwise. Remember, R is clockwise, and then S is counterclockwise, right? One letter less than S, counterclockwise, one letter less than, or clockwise, one letter less than counterclockwise via abbreviation. So this is going to be S. So now we see we have opposite R and S at every chiral center. Therefore, these molecules are enantiomers. And typically you just write enantiomers as En. If you want to spell it out, go ahead. In organic chemistry, you'll learn that we love to abbreviate a lot of things. Right? So let's go ahead and move on and look at the next question. All right. Down here, let's go ahead and analyze this. We have our parent chain of a butane, 1, 2, 3, 4 carbons. A parent chain of a butane, 1, 2, 3, 4 carbons. On the second carbon, we have a bromine here and a bromine here. On the third carbon, we have an alcohol group here and an alcohol group there. Therefore, these molecules have the same molecular formula, right? They have the same connectivity, but what's different is going to either be their spatial arrangement. So let's go ahead and analyze this to see if we have opposite R and S at every chiral center. Now, where are our chiral centers? We know that this is a carbon here, and this carbon here is connected to a hydrogen. It's connected to a bromine. It's also connected to this whole entire thing, which is completely different than this methyl group here, right? Remember, we're analyzing this central carbon right there, right? Therefore, this would be a methyl group, a hydrogen, a bromine, and something completely different. Therefore, we have 4 different things around our carbon, so this is our chiral center. Right? Same thing over here. We have a methyl, a hydrogen, and then hydroxyl group, and then this whole thing right here. Right? That whole thing right there is completely different. Right? And we know that the same thing is going on in this molecule. Therefore, we know that there's probably going to be some spatial orientation, differentiation going on in these 2 molecules. Right? So let's go ahead and do the same thing in terms of highest priority. We can start off with the bromine. We know this is going to be 1, right? And then what's next? So we start off with a carbon, bromine versus hydrogen versus carbon versus carbon, right? So we know this is going to be, bromine is going to beat the carbon and the hydrogen, so it's 1. Next up, we have a carbon versus a carbon. But then what's next? We have a hydrogen versus an oxygen. Therefore, this is going to be 2. And then this is going to be 3, and of course this is going to be 4. We go in that direction, therefore this is clockwise, so this is R. But what do we see about our hydrogen? It's on a dash. Our lowest priority group is on a our lowest priority group is on a wedge, right? If our lowest priority group is on a wedge, therefore that means we have to switch from an R to an S, right? Now let's go back here and do the same thing for the bottom part, right? So we know that this chiral center is going to be noted as an S. We have a oxygen versus a carbon versus a carbon versus a hydrogen. Therefore, this is going to be 1, right? Carbon versus carbon, but we didn't know that this is going to be a hydrogen versus a bromine because we have a carbon versus a carbon. Therefore, it's a tie. Right? If that's a tie, then this is going to be a hydrogen versus bromine, so this should be 2. And then this is going to be 3, and then of course 4. So this is going clockwise as well. But what do we know? We have our hydrogen on a dash, therefore we do not have to invert the stereochemistry. So since this is going clockwise, this will stay as an R. Right? Now let's go over here and do the same thing and compare to see if these molecules are going to be enantiomers or diastereomers or the same molecule. Right? So same thing over here. We can start with our bromine because we started with our bromine right here, right? So we have 1. We know this is going to be 2. It's carbon versus carbon, right? So then we move on to oxygen versus that implicit hydrogen, right? So this is 2, this is 3, and this is 4. This is going counterclockwise, but our lowest priority group, our hydrogen, is on a wedge. Our lowest priority group is on a wedge. Even though this is going S, or counterclockwise, we then know that we have to invert the stereochemistry to R, right? Now let's do the same thing over here, right? We know this is oxygen versus hydrogen versus carbon, so this is 1. Then we have carbon versus carbon, so we move on to the next atom. Hydrogen versus bromine, so therefore this is 2, then 3, and then 4. So this is going in the counterclockwise fashion as well. So this is going to be S, but what do we know? Our hydrogen, our lowest priority group, is on a wedge. So if this is S, then this has to switch over to an R. Now let's clean this up a little bit so we can take away some of these numbers that are here. And now let's analyze this, right? We have an S versus an R. So we had an opposite R and S from R to an S in terms of where the chiral center is for the bromo group, right? Now let's go ahead and look at the hydroxy group. We have an R and we have an R. So here we see that we do not have opposite R and S at every single chiral center. What do we know about enantiomers? Enantiomers must have opposite R and S at every single chiral center. Because these do not have opposite R and S's at every single chiral center, these molecules are therefore referred to as diastereomers. All right, so these molecules would be a diastereomer. And now we've done those 2 problems. We've looked at how these molecules are enantiomers. These molecules are diastereomers. We know how to differentiate between identical molecules and also different molecules. So now we've covered every topic you need to know for your isomers in terms of your quizzes and in terms of your tests. So now you should be fully prepared. If you still are having a little bit of trouble and difficulty, please go back and rewatch the first video, come back and watch the second video as many times as it takes for you to properly understand how to tackle these problems. I hope this has helped you, and we'll see you next time.